No sound.
A mixed radical has a whole number, which we call the coefficient. Shouldn't be a new word for you, coefficient. And a radical. So an example of a mixed radical, for example, could be 3 root of x. 3 times radical x. 3 times the square root of x. Notice all the vocabulary I used in there. We call it a root, we call it a radical, we call it a square root. All mean the exact same thing. Another example could be 4 times the root of ab. Four root ab, or 4 square root ab, or 4 radical ab. It could be 17,000 root 5. 17,000 times the root of 5. All of those are called mixed radical. Why? Because they have a number up front. If it's got a number up front that we call a coefficient, that's a mixed radical. What do you think an entire radical is? Yes. It doesn't have a other than 1. So has no coefficient. Other than 1. An example could just be the root of 17. That's called an entire radical because what's in front, we don't see it, but we know it's there. The imaginary 1, right? That's the only coefficient an entire radical has, is just that 1 tucked in front. Another example could be root of x squared. Could be the cube root of a, for example. So what we're going to practice today is going from mixed to entire, entire to mixed, and then tomorrow I'll tell you why we need to know this. Just like you do with fractions. You practice converting mixed to improper, improper to mixed, and then we were like, hey, we need this for adding and subtracting. That's all we're doing today is just practicing the how. We're not going to really get into the why till tomorrow. So first thing we're going to do is change -3 cube root of 2 to an entire radical. Let's just review. What does that mean, entire radical? No coefficient. So what it's saying is that -3 cannot be out front. That -3 cannot be there. The only number we can have out front is 1. Steps first or example first? Ooh, example first. No one ever picks example first. Kind of excited. I'm going to do the first one here off to the side. And what I'm going to do is I'm going to take that -3 and I'm just going to shove him right under that radical. Well, that's right. I'm just going to move him. I'm going to put him under there, and then I'm still going to have that 2 that was hanging around there. Well, the only way I can stick him under there is if I give him the exponent that's equal to the index of the radical. The only way I can stick him under there is if I give him the exponent that is equal to the index. So I'm going to bracket that -3 that I just moved, and I'm going to give him the exponent of 3. And then we're just going to simplify. So BEDMAS says I'm going to do this bracket first, so the exponent. So -3 times -3 times -3 is -27. And I still have that 2 that I'll deal with in a second. And now I'm just going to multiply -27 times 2. Do 20 times 2 and do 7 times 2 and then smush those together. -54. And I'm grabbing my red pen because we just need to make sure if this was a cube root in the beginning, what does it have to be all the way along? A cube root. So I'm just going to stick that little 3 in here just so we remember that it's not a square root, it's a cube root. Was that what you were going to ask me? You can't have a negative square root. As long as the index is odd, you can have a negative. Oh. Grab your calculators. I want you to calculate for me the decimal value of negative 3 cube root 2. So you're going to type negative 3 first. And then you're going to go in your math menu, and there's a cube root in there. And then you're going to put a radicand of 2 and then hit equals. So I want to know what is the decimal value of negative 3 times the cube root of 2.
Negative 3.7.
Just looking for confirmation. Ooh, nice. It does have a bunch of decimal places? So give me a whole bunch of decimal places. Negative 3 point.
7, 7, 9, 7, 6, 3, 1, 5.
Okay. The next line, I want you to do the cube root of negative 54. So again, go back into your math menu, pick up the cube root, do negative 54 equals. Exactly the same thing. Like, that's crazy when you look at these because they look so different. They're the same value. I have not changed what their value is. All I have done is change what they look like. It's like if I gave you 5/4 and 1 1/4. They look very different, but they're both equal to 1.1 or 1.25. Same deal with this. I'm not changing the values. I'm just changing what they look like. How are we doing so far? Step number 1. Move the coefficient under the radical move the coefficient under the radical and give it the same exponent as the index. Move the coefficient under the radical and give it the same exponent as the index. Second and last step, simplify the radicand. Simplify the radicand. What's a radicand? All that stuff underneath that root sign. Let's practice some more. Change 2a to the 4th times the square root of a to an entire radical. Now you need to be really careful and you need to have really, really good eyes to know what is that for. Is that an exponent on a or is that an index of the radical? How do we know it's an exponent on a? It's not above the little guy. Which, by the way, where does the symbol come from, you may be asking yourself? Well, initially it was an R for radicand, and then as the typewriter came along, they couldn't get the R over top of the X, so they invented a whole new symbol. But originally it was an English letter R, R for radical. Cool. So just note this is an exponent. It's not the 4th root, otherwise it would be under that little tail at the beginning of the radical. Not like that, no. So I'm going to keep that big square root, and I'm just making it long because I'm about to put some stuff under there. I'm going to grab that whole 2a to the 4th and stick them under. I'm still going to have that a that was hanging around, so I like to put a little multiplication sign just to remind myself eventually I'm going to have to multiply. But then I got to bracket this guy, and what exponent do I have to give it? 2. Why an exponent of 2? Because it's a little imaginary index that we don't see, but we know a square root is an index of 2. So I moved him under the radical, gave him the same exponent as the index, and now I'm just going to go to step 2, which is simplifying. This is an exponent law from grade 9 that says if you have a bunch of stuff and you have an exponent, what do we do with that exponent? We apply it to everything in the bracket, so it's been given to everything. So this is going to be 2 to the 2, which I'll evaluate in a second. Yes, I know it's 4. I'm just showing you step by step what we're doing. A to the 4th to the 2 means I have 2 exponents, which means I'm multiplying. 4 times 2 is 8. And then I still have that a hanging around, which I'll deal with him in a second. And now, because I'm left brain, it bothers me that my root sign was that big when I didn't need it to be. Now I'm just going to evaluate what is 2 to the 2. So if you can jump right from here to the 4, I'm fine with that. I'm just showing you in the first example where the 4 is coming from. Here I have 2 bases that I'm multiplying. When I'm multiplying bases, what do I do with the exponents? add them. So this is a little imaginary 1 that we don't see, but we know it's there. So if I have 8 a's and I have another a, how many a's do I have? 9. So I have the root of 4a to the 9. How do I know it's an entire radical? Because there's nothing outside except for the imaginary 1. For which values of the variable is the radicand defined? You're going to find this in almost every homework question. Kind of. So we have this issue that actually Brad brought up at the beginning. He was like, wait, square root can't be negative. And I was like, it's okay, we'll talk about it in a second. Remember last year, square roots can't be negative, square roots can't be negative, square roots can't be negative. And why is that? Why can a square root not be negative? Right, so 3 times 3, 9. So square root of 9, not a big deal. Negative 3 times negative 3, 9. Can I ever get the square root of negative 9? If you're imagining numbers, we won't go there. But there's no way to get a negative square root. So what this question is asking is, what kind of numbers are okay that this is going to be positive, and what kind of numbers is this not okay? What kind of letters or numbers for A are going to work and which are not going to work? Grab your red pens, because this is the way you're going to do every single question. You're going to grab the radicand, and you're going to set it equal to or greater than 0. What we're saying is the radicand has to be positive. They're always going to work this way. Every time you see this question, you're going to grab whatever the radicand is, and you're going to say it has to be greater than or equal to 0. So in this case, I'm going to grab our 4a to the 9 and say that it has to be greater than or equal to 0. And then the last step is just isolating the variable. And so this just becomes a little equation. How do I get rid of a coefficient of 4? What's the opposite of timesing something by 4? Dividing by 4. So if I divide by 4, I'm going to end up with my a to the 9. I'm still going to have the greater than or equal to sign. What's 0 divided by 4? How do I get rid of an exponent of 9? What's the opposite of squaring, for example? It's a 9th root is what I'm going to do. Because this is 0, all you need to know is what's going to happen if I 9th root it. It's going to remain a has to be greater than or equal to 0. That is answering the question for what values of the variable is the radical defined. It's telling you a has to be a positive number. It's saying if we stick in any negative number, this is not going to work. This question will become the bane of your existence because they're going to ask it over and over and over. It's always going to be these same 2 steps. Radical greater than or equal to 0, solve for the variable, get it by itself. Questions? Are you here or higher? Good. One more practice. Convert to an entire radical. You tell me, what's step number 1? Shove it all underneath. So I'm going to put that square root. I'm going to take that 4a, put it underneath. And then I'm just going to put that AB at the back. But that's only half of step 1. What's the second half of step 1? Yeah, the. What's the vocabulary word? Exponent is the same as the index. What's the index for this? It's a little imaginary too. So there's step 1, put it underneath, it's part of the radicand, put the same index as an exponent. Now we just need to simplify. I'm going to do it in less steps this time. 4 squared, 16. A squared squared, a to the 4. B squared, B squared. And then I still have that little AB hanging around the back, which I'll deal with him in a second. Okay, so all I did was square every piece because of that index of 2. Now I'm just going to simplify it. 16 is the only number I have. How many a's do we have? So if I have 4 and then 1 at the very end, how many a's? A to the 5. And then I got a b squared, and another b is going to give us b cubed. There's changing to an entire radical. Square root of 16 a to the 5b cubed. Why? That will come tomorrow. We're just practicing the how today. Okay, here, again, here's okay. Now we're just going to go backwards. We're going to go from entire radicals to mixed radicals, and this is really called simplifying radicals. We actually like those coefficients outside. You started these last year in grade 10, and I know for some of you it's been over a year since we did it, so let's just review. How did you simplify root of 50? Does that even seem familiar to you? Okay, so I'm going to show you the method I use. I don't know if this is the way your teacher showed you last year. If you have a different method, go for it. There's nothing wrong. I do what's called the factorization method. So we take the prime factorization of the radicand. We group what's called identical prime factors. Then we evaluate the grouped radical, and we simplify the answer. And I'll explain all that with the example in a second. Yeah, it's factor tree. It's exactly what it is, factor tree. So what I want to know is, let's do the prime factorization of 50. And I always do this off to the side. This should kind of look familiar from grade 10, maybe a little fuzzy. So you grab any two factors of 50, doesn't matter what you start with. 2 and 25. Are either of those prime factors? 2, so I circle that one because now that tree of the factor tree is done. 5 times 5. Are any of those prime? Both. So that tells us we're done the factoring because all the branches end with the circle. Okay, so that's called prime factorization. So I'm going to take root of 50 and I'm going to say, well, it's the same thing as 2 times 5 squared. Still with me? Prime means that the only factors are 1 and itself, but 1 doesn't count. So the only factors are 2 are 1 and 2, and the only 5 are 1 and 5. There's nothing else we can break it down into. You still with me here, what I've done? Now I'm just going to split these apart. There's a law in math that says if you're multiplying in the radicand, we can break them apart. So I'm going to make this into the root of 2 times the root of 5 squared. I'm just breaking that radicand into 2 pieces. Can I evaluate the root of 2 evenly? Is it a perfect square? No, so I'm not going to touch it. I'm just going to leave it in a second. What about 5 squared? What happens if I root something that has a squared? They cancel, and that's the point of why we're doing this. So the root and the squared are going to cancel, and what does that leave us? 5, and then I just have the root of 2 in the background. That's converting to an entire, or a mixed radical. That's simplifying. You should have seen that last year. Does it kind of look familiar? All we're going to do, if you look down, is we're going to start adding cube roots and some variables. But the process is the same what you did last year. So if this was your method, great. If you had a different method that works for you, that's fine. There's nothing wrong with that. I'm just showing you one method how to do it. Like I said, all we're doing it now is you didn't do cube roots last year, and you didn't really do exponents, or do variables. Okay, so I'm going to take 105, or 108, sorry. And let's start prime factoring. Again, doesn't matter what you start with. Pick any 2 factors that you know multiply to give us 108. 9 and? Somebody want to check that? Are either of those prime? No. So if your brain didn't go to 9 and 12, that's fine. You could have done 2 and 54. That's fine. Doesn't matter which ones you start with. Okay, if this isn't prime, then we need to break them down. What can I break 9 into? 3 and 3. Are either of those prime? So let's circle them because that tells us that branch is done. 12. 3 and 4. Are either of those prime? 3, so that branch is done. 4 we can break down into 2 and 2. And so we know that 108 is the same as 3 cubed times 2 squared. I just counted up how many 3's and how many 2's. Yes, ma'am. Yeah, I'll just tag the negative when I go back to this side. So I'm going to keep my cube root. I'm going to keep that negative that was there. And I'm just going to replace with the prime factoring, which is 3 cubed times 2 squared. And then what I want to do with this A to 11 is I want to break it up into groups of 3. And why 3? Just because I'm dealing with a cube root. So I can take 3 once out of 11. Can I take it out twice? Yes, because that would be 6. Can I take it out 3 times? That would be 9. Can I take it out 4 times? No. So you can either break it all at once or you can just break it up. I'm going to show you both ways. I'm going to say that this is a to the 9 times a squared. All I'm doing is bringing out the highest multiple of 3. You could write this as if you want to, as a to the 3 times a to the 3 times a to the 3 times a squared. It's completely up to you which way your brain sees it. Now, because we're dealing with a cube root, what I do in my head is I circle everything with a 3 or everything with a multiple of 3. So either my a to the 9 or my a to the 3, a to the 3, a to the 3, completely up to you. Because those are the ones we're going to end up bringing out front. Anything not circled are the ones that are going to stay behind. So if I take a cube root of a negative 3 cubed, what happens with the root and the exponent of 3? They cancel. So all I'm going to have out front is that negative 3. That's the purpose of what we're doing, is the root cancels the exponent. Either this a to the 9 or the 3 a to the 3's doesn't matter. What's going to happen with the 3 and the 9? Kind of. It's a division. So 9 divided by 3 gives us a to the 3. Or we can cancel, 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 which leaves us a times a times a. And what's a times a times a? A cubed. Can I just finish this example? Okay, so I'm going to repeat that. You either do the 9 divided by 3, or if you're this way, you cancel the 3 3's and then multiply those 3 a's together. What's everything that's left? So what did I not circle? The 2 squared and the a squared. We're going to do some more examples, so don't panic if that's a thumbs down. Hello, ladies. Come on in. What would you, if it was just 40, let's just pretend, what would you do to it? You would do factor tree, just like we did with every other number. So let's do factor tree for 40. Do you have to use a tree? No, you can do it any way you want. You just need to prime factor. What's the prime factoring for 40? 2 cubed times 5. And now we just double check, do I want groups of 3 or do I want groups of 2 or do I want groups of 4? What's going on here? Groups of 3, why? Because of this little 3 out here. So this one's good. I don't need to change it. I can leave them as 2 to the cube. Now I'm going to do the same thing with 81. So if there's 2 numbers, I'm just going to do them separately for now. I'm not going to panic. We'll worry about the fraction in a second. 81 breaks into 9 and 9. And 9 and 9 breaks into 3 to the 4. If you'd rather have those groups of 3, what can I split this into? Okay, so coming over here, it just means I'm going to have a fraction here. So I'm going to put my 2 to the 3 times 5 on the top. And I'm going to put my 3 cubed times 3 on the bottom. So if it was a fraction in the question, it's a fraction now. I'm going to circle these guys because they're the ones that are going to end up canceling when I simplify in a second. What's going to happen to that cube root with a cubed here? Okay, so what's going to come out front on the top? What's going to come out front on the bottom? Not a trick question, just a 3. What's going to be left under the cube root? 5 on top, 3 on the bottom. You've now seen ones with variables, you've seen one with a double variable, and you've seen one as a fraction. When you do the homework, what do you think kinds of questions are going to be there? Exactly like these. So grab your example, see which one's exactly the same, put them next to each other, try to do it. Questions so far? Last thing we just need to do is ordering. Just like you did with fractions way back in grade 10, we need to know which one's less than which one's the biggest. And we're going to put them in ascending order. That's a word you need to know. I can't tell you what ascending means on a quiz, just like a coach can't come out in the field in the middle of a game and tell you what play to do. You need to know, what does ascending mean? Going up. What does descending mean? Going down. So this means from the smallest to the largest. Just like fractions, what we did is we changed them all to mixed fractions. Now we're going to change them all to entire radicals. And then we're going to put them from smallest to largest. So let's start with our 2 root 3 first. 2 is going to move under that sign. But what do I need to give him? See, now you should be able to see is why am I giving him the index? Because what happens if I were to pull him out front? It would cancel. So what I'm doing is giving it back from the canceling. That's why we give the exponent when we go backwards, because it would have canceled, so I need to put it back. And now I'm just going to simplify BEDMAS, so exponent first, 2 times 2 times 3, 12. If you were to put 2 times root 3 in your calculator and you were to put root 12 in your calculator, they're the exact same number. I have not changed their value, I've just made them look different. Then we're going to do 4 root 5. And so the 4 is going to go underneath. I'm going to give it the exponent of 2 that would have canceled when I pulled it out front. And now I'm just going to simplify what is 4 squared. And what's 16 times 5? If you're not sure, do 10 times 5 and 6 times 5, and then smush them back together. Now be really careful here. This is 3, not 3 root 8. The next one is just 3. And so I'm going to change him to a radical 2. What? Well, what is 3 as a square root? Square root of what equals 3? is 9, and that's just because I put them underneath and I give them a square and I evaluate it, which equals 9. And the very last guy is just root 8, so he's already simplified. We don't need to touch him. What was the purpose of changing these all to entire radicals? So we can compare which one is the smallest. Which one is the next smallest? Which one is the next smallest? And the last smallest? And the very last step now is we just go back to the originals. What was root 8 in the original question? Well, it was root 8. What was root of 9 in the original question? What was root 12? And what was root 80? And there is the radicals in ascending order. I don't know. I can't remember if we did this in grade 10. But I think maybe easier numbers, I think. Yeah, maybe easier numbers. You have the idea anyway. I'm just going to recap because we did a lot today. Very first thing is you need to know your vocabulary. You need to know what's that little number called that's in the root sign. What's under the root sign, what's it called? And what's the whole thing together? Second vocabulary we did is mixed radical versus entire radical. What's a mixed radical? Perfect. What's an entire radical? Perfect. Then we converted from one to the other. We went mixed to entire, entire to mixed. And the reason we did that was to be able to order them like this and know smallest to largest or largest to smallest. Give me a thumb. Where are you? Awesome. Homework is on page 120. You've got 12 minutes now, which means you're not going to have time to get through them all.